So I want to tell you about right-angle Coxeter groups that are commensurable to right-angle Artin groups. So my name is Levcovitz, and this is joint work with Pallavi Denny. So let's begin with the definition of right-angle Coxeter groups and right-angle Artin groups. So these groups are defined in terms of defining graph. Here I denote by gamma. And right. So a right-angle Artin group is a group whose generators you can associate with the vertices of the graph, and whose only relations are that two generators commute if there's an edge in the graph, in the defining graph. And we say that a gamma, which is the right-angle Artin group, with S, this generating set is a RAG system. So being a RAG system, this basically means this is a RAG with this sort of standard generating set. It's not another kind of generating set. Okay, so right-angle Coxeter groups are defined very similarly. It's basically the same definition, except that the generators also have order 2. So you have torsion and right-angle Coxeter groups. So an important theorem to this talk is one by Davis and Hennenfent, and it's that every RAG embeds as a finite index subgroup in some right-angle Coxeter group. So every RAG is actually commensurable to some right-angle Coxeter group. And the question I'm interested in this talk is the converse question. So which right-angle Coxeter groups are commensurable to RAGs? Or even more specifically, which right-angle Coxeter groups contain finite index RAGs as subgroups? And another related question is which right-angle Coxeter groups are quasi-symmetric to RAGs? And recall that if you're commensurable to a RAG, then you're quasi-symmetric to one. Okay, so now we now see that there are many examples of right-angle Coxeter groups that are not quasi-symmetric to RAGs. So the converse to Davis and Hennenfent result is not true. So the first example I want to look at is some hyperbolic reflection groups. So in this case, if the defining graph is an n cycle with n bigger or equal to 5, then the right-angle Coxeter group W gamma is a Fuchsian group. And for n equals 5, you can actually see a drawing of this action in the hyperbolic plane on the cover of Mike Davis's book. So if you, for n equals 5, what you can do is you can draw the hyperbolic, in the hyperbolic plane, a pentagon with all right angles. And you can look at the group generated by reflections about the sides of this pentagon. That group exactly is this right-angle Coxeter group. And this construction works for all n. So for n bigger than 5, you just take the appropriate right-angle n-gon in the hyperbolic plane. Okay, so from this we see that this group acts properly co-compactly on the hyperbolic plane. So therefore it's one-ended. And again, because it's quasi-symmetric to the hyperbolic plane, it's hyperbolic. But if we look at RAGs, every one-ended RAG actually is not hyperbolic and contains z-squared subgroups. So the way to see that is that if you look at a RAG with a defining graph, if it doesn't contain an edge, then there's no relations in the group, so it's a free group. So it's not one-ended. So if you're one-ended RAG, you have to contain some edge in the defining graph. But as soon as you contain an edge in the defining graph, you have a z-squared subgroup. So these are examples of right-angle Coxeter groups that are not quasi-symmetric to any RAGs, because being one-ended and being hyperbolic are quasi-symmetry invariants. So just leaving the world of hyperbolicity for 1 second, and even the world of non-relatively hyperbolic groups, there's still examples of RAGs, right-angle Coxeter groups that are not commensurable to RAGs. So one way to see this is using the divergence function. So this is a quasi-symmetry invariant, which measures the maximum rate a pair of geodesic rays diverge in the Cayley graph of a group. So it's a result of Boerstler-Charney that RAGs either have linear, quadratic, or exponential divergence. And I think it's a surprising result of Denny Thomas the right-angled Coxeter groups can have divergence of any degree polynomial. So in particular, if you pick an integer bigger than 2, such as 3 or 4, and you look at right-angled Coxeter groups with, say, cubic and quartic polynomial divergence, then those are not quasi-symmetric to any rags. So you get a whole other classes of examples this way of right-angled Coxeter groups not quasi-symmetric to rags. Okay, so what you might want to do is restrict to, say, quadratic divergence, because we know that rags and right-angled Coxeter groups have quadratic divergence. So maybe that's enough to understand the right-angled Coxeter groups, which are quasi-symmetric to rags. But even doing so is not enough. So there's another quasi-isometry invariant known as a Morse boundary. So this basically looks at the boundary, the visual boundary. Well, the topology is more complicated, but it's the boundary looking at Morse geodesics in your Cayley graph. So it's a result that rags always have totally disconnected Morse boundary. In the two-dimensional case, this is implicit in Charney-Sultan's paper, where they first defined the Morse boundary. And for the general case, it follows from Cordes-Hume. And I also want to mention the Charney-Cordes-Sisto. They give a very nice description of, they further study these Morse boundaries of rags, and they give a nice description of them. Okay, so for rags, always totally disconnected Morse boundary. But for right-angled Coxeter groups, there's actually right-angled Coxeter groups with quadratic divergence and Morse boundary with non-trivial connected components. So this is a result of Burstock. So those are right-angled Coxeter groups with quadratic divergence that are not quasi-symmetric to any rag. So what I want to do in this slide, at least, is restrict further the class of right-angled Coxeter groups. So here we'll be looking at right-angled Coxeter groups that are two-dimensional. So this means there's no 3 cycles in gamma. This also means that the Davis complex, which is the natural cube complex this right-angled Coxeter group acts on, is two-dimensional. So that's the name. These right-angled Coxeter groups are one-ended, and their defining graphs are planar graphs. So in this situation, there's actually a complete classification of which right-angled Coxeter groups in this setting are quasi-symmetric to rags. So this is the result of Nguyen Tran. So what they do is they take such a planar graph and they associate a bicolored visual decomposition tree associated to the graph. And they color this tree black and white. So they show that the right-angled Coxeter group is quasi-symmetric to some rag if and only if every vertex of the tree is black. Okay, so it doesn't really matter exactly what this tree is. We just care right now that there's a classification within this class of right-angled Coxeter groups of the ones quasi-symmetric to rags. So then you can ask, okay, we know these right-angled Coxeter groups are quasi-symmetric to rags. Are they actually commensurable to them? So that's our first result that I want to talk about, is that in this class of right-angled Coxeter groups, being quasi-symmetric to a rag is equivalent to being commensurable to a rag. So I'll talk about how we prove this. So to prove this theorem, we actually had to find a way to detect finite index rag subgroups of right-angled Coxeter groups. And that came with 2 challenges. One was to show that these candidate groups that we had were actually rags. The other challenge was to show that they were finite index. So to find these rag subgroups, we needed some kind of candidate subgroup that we hope will be rags. So these are the ones we look at. So again, gamma is a simplicial graph. So if you take 2 vertices of gamma that are non-adjacent, those correspond to non-commuting elements of the right-angled Coxeter group defined by gamma. If you multiply those 2 generators, then since they don't commute in the right-angled Coxeter group, what this will tell you is that the word ST, which is those 2 generators multiplied, is actually an infinite order element of the right-angled Coxeter group. So since rags do not have torsion and they're generated by infinite order elements, this is a good place to start. These are the simplest infinite order elements of right-angled Coxeter groups, and we hope that a collection of them will generate a rag. Okay? So there's a natural correspondence between these non-adjacent vertices of gamma to edges of the complement graph of gamma. So recall that a complement graph is a graph with the same vertex set as gamma, but you have an edge exactly when you don't have an edge in gamma. So that's why it's the complement graph. So there's a natural correspondence between these pairs of non-adjacent vertices of gamma and edges of the complement graph. Okay. So what we're going to do is we're going to pick a subgraph of the complement graph, which we will always denote by lambda. And then, so the edges of lambda now correspond to infinite order elements of the right-angled Coxeter group. So we can look at the subgroup of the right-angled Coxeter group generated by these infinite order elements. And we denote the subgroup by G lambda. So G lambda is, we hope, will be a rag. Okay? So here's the more formal definition. So you take a subgraph lambda of the complement graph, gamma, and then you look at the subgroup G lambda of the right-angled Coxeter group generated by the infinite order elements corresponding to the edges of lambda. I know there's a lot of graphs involved, but feel free to pause this video if you want to. So if G lambda with this generating set turns out to be a rag system, then we say G lambda is a visual rag. So visual because you can actually see this from the defining graph. Okay, I should say that we were not the first ones to study visual rags. So they were first studying Lefforge's thesis, and in the following slides, I'll tell you about what his results were, some of his results. So they were first studied there. So before we get into those, let me just give a quick example. So here we have a right-angled Coxeter group with defining graph gamma. And then we look at a choice of lambda in the complement graph. So in this case, lambda has two components and is shown in red and blue. So for the remainder of the talk, I will use the convention that the graphs drawn in black correspond to gamma, the defining graph of the right-angled Coxeter groups. And then the colored graphs correspond to lambda, the subgraph of the complement graph. Okay? And the number of components of lambda and how they interact with each other will be important in what's coming up in the future slides. So each component of lambda will be shown in a different color. So here, this lambda drawn here has two components, and it's drawn in red and blue. Okay, obviously we can't pick lambda randomly out of the complement graph and expect the associated group G lambda to be a rag. There could be relations that we're not seeing. So what I want to do now is discuss some necessary conditions on lambda for this group to be a visual rag. If this group turns out to be a rag, these conditions have to be satisfied. The first three of these are due to Lefforge. And these conditions are naturally classified by the number of components involved. So we're going to have conditions involving 1, 2, and components, for instance. Okay, so first let's do the single component conditions that you only have to look at one component of lambda. The first one is pretty straightforward. Is a condition that lambda does not contain any cycles. So if you want G lambda to be a rag, lambda cannot contain any cycles. And this example I drew before, that lambda did not contain any cycles. Condition R2, the second single component condition, is that given a path in lambda with endpoints P and Q, then P and Q do not span an edge of gamma. So if you take a path in lambda, you look at its endpoints, those endpoints correspond to generators of a right-angled Coxeter group, and you want them to not be commuting. So let me show you why condition R2 is necessary. So this is due to Lefforge. This was in his thesis. So if lambda does not satisfy R2, then G lambda is not a rag. Let's remember what it means to not satisfy R2. So this means there's some path in lambda. So let's say traverses vertices S1 through Sn. And the endpoints of the path, S1 and Sn, are non-adjacent, are adjacent vertices in gamma, because this does not satisfy R2. And so the vertices S1 and Sn commute in the ambient right-angle Coxeter group, W gamma. So since we have this path in lambda, we have those edges of lambda correspond to generators of G lambda. So if you follow along the path, we have a generator here, S1 times S2, then a generator S2 times S3, and so on, Sn minus 1 times Sn. What we do next is multiply all these generators together, and recall that in right-angle Coxeter groups, generators have order 2. So for instance, this S2 and this S2 cancel. When we multiply everything together and cancel things out, you get that the element S1 Sn is in G lambda because it's the product of generators in G lambda. Okay. But then you do another simple computation, which is you square S1 and Sn. And since S1 and Sn commute by the condition, by how we pick this path in the beginning, it follows from a simple computation shown here that the word S1 Sn, the element associated with this word, has order 2. Okay, so now we recall the rags are torsion free. They're actually K-pi1 groups. So since G lambda contains an order 2 element, it cannot be a rag. This is the proof that R2 is a sufficient condition. Use the Lefort. Okay, the third condition is a 2-component condition. Let's look at the picture. This condition basically says if we see a square in gamma, such as this one, whose vertices are between 2 components, shown in red and blue here, then if you look at the convex hull in lambda of the square, these are these vertices shown in black, then what actually has to happen is that if you see something like this, the condition tells us that you actually have to see edges between the vertices in the red component and the vertices in the blue component in those convex hulls. So recapping, if you see such a square going between 2 components, then in their convex hull, you actually have this whole join subgraph of gamma. Condition 3. So what Lefort showed in his thesis, his theorem, is that R1 and R3 are necessary. So if G lambda is a rag system, then lambda has to satisfy conditions R1, R2, and R3. So we saw proof why R2 is necessary. You can similarly, he proves that R1 and R3 are also necessary. So there's natural questions. Is that, are we done? Are there more conditions? So basically, what is a full set of sufficient and necessary conditions for this thing to be a rag? And again, what we're interested in, or one of the things we're interested in, is when are these subgroups or these visual rags actually finite index? Because we want to get things commensurable to right-angle Coxeter groups. Okay. So no, we're not done. There's one more condition. So this is another 2-component condition, which we call R4. And the picture tells a million words here. So this says if you have a cycle in gamma, such as the one drawn in black here, that bounces around between 2 components. So here it's bouncing between the red and blue component of lambda. And then if you focus on one of the edges of the cycle, say this bold black edge here, what this condition tells us is that you actually have to contain a square in your graph gamma. The square here is drawn in the dotted lines, which contains this edge, and whose vertices are in the convex hull of the cycle. So here in the picture, the vertices of the square lie in the convex hull of the cycle. So yeah, the conditions tend to get more complicated. So the first a theorem I want to share with you is that we actually obtain a complete characterization of these visual rags when lambda has at most 2 components. If we restrict to these lambdas with 2 components, then G lambda is a rag system if and only if these conditions I shared with you, R1 through R4, are satisfied. So our contribution here is finding this new condition R4, showing that it's necessary. And what took a lot of work was showing that R1 through R4 are sufficient conditions. In other words, if you have a lambda, 2 components, satisfying R1 through R4, then it is in rag. There's no other hidden conditions. So I want to share with you some ideas in this proof of sufficiency. I can't give you the whole proof, but I want to show some ideas and maybe some pretty pictures. So what's the setup? So here we have a lambda, which is a subgraph of the complement graph, satisfying conditions R1 through R4. So to prove sufficiency, we need to show that G lambda is indeed a rag. Okay, so how do we do this? Well, if G lambda is a rag, we actually know what rag we want it to be. We want it to be the rag whose generators are the same as generators G lambda, and with commuting relations exactly when those generators commute. What we can do is form what we call the commuting graph delta here associated to the generators of G lambda, or in other words, the edge set of lambda. Remember, the edges of lambda correspond to 2 non-adjacent vertices in gamma, and those correspond to infinite order elements of your right-angled Coxeter group. So we have a natural candidate for a rag is A delta. And we want to show that G lambda is isomorphic to A delta under these conditions. So just by definition, we have a map from A delta to G lambda, which sends generators to generators. And this map is surjective. That's just by how we define things. So our goal is to show that this map is injective. So in other words, there's no relation to G lambda that you're not seeing in the right angle Artin group you want it to be isomorphic to. So how do we prove injectivity? Well, we take a word in G lambda. Remember, a word in G lambda. So here R1 through Rn are generators of G lambda, and each Ri is decomposes as Si times Ti, where Si and Ti are non-adjacent vertices of your graph gamma. And what we do is we form a disk diagram in the right-angle Coxeter group with boundary W. So we form a loop with the word labeled by the word W. So it goes S1, T1, S2, T2, etc. And we form the Van Kampen diagram, or this diagram, associated to that loop. And since we're in a right-angle Coxeter group, this diagram, or Van Kampen diagram, is built up of only of squares. So there's no other types of cells. And what you can do in that situation is look at dual curves dual to edges in the disk diagram. So what you do is, let's say you take an edge in the boundary, so like S1, you look at a square containing it, and you start just traversing opposite edges of squares containing that edge. So similar to the idea of tracks or dual curves or hyperplanes. So again, focusing on this generator S1, here's the dual curve, or what I'll be calling hyperplane, go to S1, and you follow it along until it hits the boundary again. And it'll hit some other generator, SJTJ. Okay? So what do you want to do when you see this picture is you want to take the dual curve dual to SJ here and continue that along. So you do that. And again, you hit another generator. And you keep repeating until you get what looks like a cycle of hyperplanes. So we call this a chain of hyperplanes. And to each edge of the boundary, you get one of these chains of hyperplanes. So then we don't stop there. We do this construction for all the edges of the boundary. So this diagram decomposes into chains of hyperplanes as shown here. So the idea of the proof now is to use a conditions window, R1 through R4, to try to deduce properties of these hyperplane chains in terms of this diagram. So the first thing you notice when you're working with these is that these hyperplane chains, which I'm just calling chains here on the slide, they correspond to paths in lambda. So each hyperplane, there's a label associated to it, which is basically the label of the boundary edge it's dual to. And if we read off the labels of the hyperplanes in the chain, that actually corresponds to a path in lambda. Okay? And from that, we can color code the hyperplanes. So each hyperplane chain corresponds to a path in lambda, so it's in the component. So we color the hyperplane chains, here in this picture drawn red and green, depending what component they're in. And there's more patterns you can notice from these configurations. The condition R2 actually guarantees that hyperplanes of the same colors do not intersect. So the picture really does look like the one drawn. So, so these hyperplane chains do not self-intersect, and hyperplane chains of the same color are disjoint from each other. So you get a picture like the one shown. And then you start digging deeper, and you start saying, okay, what about a hyperplane chain that intersects a different hyperplane chain? Like this green one here on top intersect this red one. And if you go along their intersections and you look at the labels, what you notice is that actually corresponds to a path in gamma in this case, which bounces between two components of lambda. So you actually, it's one of those paths bouncing between two components of lambda, very similar to the types of paths we saw in the conditions, condition R4 actually. Okay, so I'm not going to give you the whole proof, I just want to share some elements of it. So the idea of the proof is to use these conditions R1 through R4 to deduce properties of these hyperplane chains. And then you can show that you can, because of R1 through R4, you can perform moves to these disk diagrams, which corresponds to relation in the RAG. And these moves sort of reduce the complexity of the disk diagram. You're going to do this diagram of lower complexity. And when you repeat these moves, eventually you arrive at a contradiction by showing that the original word you've shown can be reduced in the RAG using RAG relations, which is a contradiction to our choices. Okay, so a natural question is, remember all of this is for the condition that lambda has two components, at most two components. So what about more than two components? Well, unfortunately, things keep getting worse. So I'm not going to give you we found other necessary three-component conditions. I won't list them all, but I'll just show you a picture of one. So here we have three components shown red, blue, and green of lambda, and a certain configuration as shown here. So what we found is that if this configuration is present in your graph, then it actually implies that gamma must contain a triangle. Sorry, if this configuration is present and G lambda is indeed a RAG, then gamma must contain a triangle. So this is another necessary condition for more than two components. But remember, we're mostly interested in finite index subgroups of the Rencontres groups. So we can try to focus on finite index things. So now we're going to focus on Rencontres groups. They're two-dimensional. Remember, this means there's no three cycles in gamma. And we want to focus on finite index visual RAGs. And in that case, we actually get a complete classification of finite index visual RAG subgroups. So here's the theorem. So again, if W gamma is two-dimensional and lambda is some subgraph of your complement graph, then G lambda is a finite index RAG system, so it's both finite index and actually a RAG. If conditions R1 through R4 are satisfied, there's the conditions I shared with you before, and then you have these additional conditions F1 and F2. So basically, the work in this theorem was that we found conditions F1 and F2, which guaranteed that this G lambda is finite index. And one important tool to do this was I have another paper with Denny, where we find conditions for subgroups of right-angled Coxeter groups to be finite index or not. So we use some of the machinery developed in that paper to find these conditions F1 and F2. Okay, and now why is this slide called finite index miracle? So I think it's a miracle because once you know conditions F1 and F2, and you know that your right-angled Coxeter group has to satisfy condition F1 and F2, and if this if lambda actually contains 3 components, then what you can show is that it must contain a configuration similar to this one. And as I said, this is an obstruction because if you contain such a configuration and you're a rag, then you must necessarily contain a triangle. So if you restrict to 2-dimensional right-angled Coxeter groups, you actually, what we've shown is that you actually, lambda has to have 2 components. That's why it's a miracle, is because when we restrict to finite index things, and you know these conditions F1 and F2, you know lambda has 2 components, and you can use a prior theorem as stated about 2 components visual rags. And we're thankful for that because these conditions just seem to be getting more and more complicated. And by the way, we don't even know, without the finite index assumption, what is a full set, what should be the full set of necessary conditions? And I think that's an interesting question. So anyways, we have this characterization of finite index rag systems, or visual rags, in 2-dimensional right-angled Coxeter groups. And let me just quickly explain what conditions F1 and F2 are. So F1 is that lambda contains every vertex of gamma. So you sort of expect this condition because if the generating set of lambda didn't use one of the vertices of gamma, you can intuitively imagine that it will not be finite index. It doesn't, because it won't contain any the words in the right-angled Coxeter groups containing that vertex. So he misses sort of too many words. And there's a small caveat that with the exception, you don't have to contain vertices that can meet with every other vertex. This is a small technical detail. I wrote it here in small font. And then the second condition is that given 2 vertices in lambda in 2 different components, you always have a path in lambda bouncing between those 2 components, between those 2 vertices. So those are the 2 conditions. Okay, so let's recall what I was talking about in the beginning of this talk, which was right-angled Coxeter groups commensurable to rags. That's this theorem I said we had, that if the right-angled Coxeter group is 2-dimensional one-ended, and the defining graph is planar, then it's quasi-symmetric to a rag if and only if it's commensurable to a rag. We'll talk about how that's proven, knowing what we know now. So remember, by Nguyen Tran's work, we have a graph theoretic description of right-angled Coxeter groups with these planar defining graphs that are 2-dimensional. So right-angled Coxeter groups in this class, which are quasi-symmetric to rags. And the description was in terms of these visual decomposition trees. So what's the strategy now? The strategy is that we want to pick lambda, a subgraph of such a right-angled Coxeter group, satisfying our conditions R1 through R4, F1 and F2. And the way we guarantee that you can pick such a lambda is we induct on Nguyen Tran's visual decomposition tree. So step by step, we pick the subgraph lambda by taking bigger and bigger sections of this tree, and in turn, taking bigger and bigger sections of the defining graph. So this is actually just this part of the proof. Once you know the classification of finite index visual rags, this part of the proof is just completely graph theoretic. So it's like 2 pages of graph theory, just showing that you can pick these graphs lambda satisfying our conditions R1 through R4, F1 and F2. And it was actually kind of fun to do. Okay, But once you know that these subgraphs exist, satisfying conditions R1 through R4, F1, and F2, for the right-angle Coxeter groups quasi-symmetric to rags in this class, then by our previous theorem, we actually know that these right-angle Coxeter groups contain a rag that's finite indexing it. This basically this visual rag we were talking about before, d lambda. So we know that these right-angle Coxeter groups are actually commensurable to rags. Okay, and that's the strategy of showing this theorem here. And before I end, I just want to say that there's a lot of interesting questions left in this direction of research. So for one, I said that we classify the finite index visual rags into two-dimensional right-angle Coxeter groups. But if you drop the finite index assumption, then you seem to be getting more and more complicated conditions. So it's an interesting question figuring out what the full set of necessary conditions are, and if there's some pattern to them as you increase components. Another interesting question is, so there's no particular reason we focus on this class here in this theorem of right-angle Coxeter groups, the ones with planar graphs, except we already knew those were quasi-symmetric to rags by Newton transversal. So I believe that these visual rags can be used to show a whole lot more classes of right-angle Coxeter groups are commensurable to rags. So there's a lot to explore there. And in general, it's just very unknown which right-angle Coxeter groups are commensurable to rags. As I showed in the beginning of the talk, it's a complicated situation, and we don't seem to have fine enough invariance to distinguish which ones are commensurable to rags. So I think that's a very interesting question too. Okay, so I'll end my talk there. Thank you very much.